Hello everybody, today we will be making some funny copper oxides. First we must heat salt water in a pan to make a heated brine. Essentially what we are doing today is the opposite of what normal people will do, where rather than taking rocks out of the ground and turning them into metals that are pure, we will be taking pure metals and turning them into rocks that belong in the ground. This is so revolutionary. We are taking steps backwards here. This is amazing. This brine will be used to turn copper into copper oxide. Many people wonder why I like copper oxide or metal oxide so much, and to be honest, I just quite like the way they look. Iron oxide is a very pretty red color. I was wondering if copper oxide would be a beautiful green. However, later in the video we discover that this is not the case, that the sample that I've made, the pure sample I have, is red, just like my iron oxide. I had to add additional water to the pan to dissolve undissolved salts. This caused the ratio to be ruined. Having more salt increases the results. What I mean is, your reaction is going to be much faster, much more efficient, and last longer if you have more salt than water. But all of that salt must be dissolved in the water. Undissolved salts do not get electrolyzed very well. This acts as an electrolyte solution, which can electrochemically oxidize metals. Doing this can produce many different chemicals too. Many well-known ones such as sodium hydroxide, which is commonly used as drain cleaner, and bleaches like sodium hypochlorite and hypochlorite. This all depends on how you have the reaction set up. In this case, we have copper at the anode. This attracts negatively charged ions called anions. These can include chlorine, hypochlorites, hypochlorites, hydroxides, and oxygen. The cathode, which is graphite, will be attracting positive ions. This will include sodium and potentially other positive ions. As positive ions and negative ions interact in the mixture, the formation of sodium hypochlorite, hypochlorite, and sodium hydroxide will occur. In the case of bleaches, sodium hypochlorite and hypochlorite, they will be catalytically destroyed at the anode. This causes it to oxidize much faster. I have read quite a bit about this, or more specifically the production of hypochlorites, hypochlorites, and other bleaching agents. It is important for hypochlorites that are liquid, or hypochlorites that are liquid, to not be stored with any metal impurities. To be more specific, it cannot have nickel, iron, or copper. I think there may be another one, but I'm just forgetting what it is. As far as sodium hydroxide goes, as it is produced, sodium hydroxide should react with the copper. However, I do not notice this until later on in the video, as this is supposed to make a blue liquid, and in fact I do spot this blue liquid at the end. Now I would like you all to listen to this beautiful sound. Since we are not outdoors when doing this, you can hear the amazing sound of the bubbles. These bubbles are gases. Thankfully, hydrogen is a plus and chlorine is a minus. If hydrogen and chlorine were together, they might react to form hydrogen chloride. This could be formed with a UV light, or by burning hydrogen in the presence of chlorine. This gas could then be absorbed into water to form hydrochloric acid. This acid could be used in many things. However, its formation is not ideal here, as this setup is not designed to handle it, and it would just be vented into the room. It would then be absorbed into the moisture in the air, and could then become very dangerous. You're probably wondering, where on earth is the chlorine coming from if it's being turned into bleaches? Well, remember, as I said earlier, the bleaches are being destroyed at the copper. This results in their components either being stuck in the solution, or becoming gases and rising out. The same can be said for the hydrogen, which is forming at the graphite. Although it is not forming compounds, it's just floating out. Now I am kind of concerned seeing the final result, that maybe we have gotten the electrodes backwards for the past two experiments. This would result in me having to start over, but that is not a problem, as I find every result to be very interesting. However, just like last time, this solution did not smell bleachy, and thus I can assume that all of the bleaches were destroyed and turned into chlorine, which was vented into the air. You can notice that our solution has gone from being perfectly clear to almost foggy orange. This kind of reminds me of industrial mining operations, in which they use gigantic lakes full of liquid metal slurries. I'm not sure what these are called, or how to describe them, but this is what the solution kind of reminds me of at this point. I think that most people who don't know what this is, or why it is so orange, would think it is very disgusting, mainly because they do not know what it is. However, I know it is a mixture of different chemicals, and is mostly just copper giving it the orange color, and to me this is very beautiful. So far, our copper oxide solution is going well. You can see here the bubbles are coming off. This is a very cool shot I got of it. Unlike most electrolysis reactions, I was not able to get a good view of the side, where you can see the bubbles. Anyway, here is my live reaction and observations about what is going on.
It's really hot. This graphite is incredibly hot. Alright, so we've discovered that the resistance going through the graphite is causing it to heat up quite substantially, actually. If we touch this here, my hand is burning. It's kind of hot. It is quite hot. I mean, I don't think there's a problem. I think it's actually speeding up the reaction. Now, the liquid is not warm anymore. It's not got any residual heat in it. But this guy right here is probably also pretty warm if the graphite is warm. Although, graphite should have a bigger resistance since it's not really a conductor. I mean, it is conducting. Yes, it does conduct, but it's not the best conductor, so it's probably got a really big resistance on it. We've gone through about 3 electrodes so far, 2 small, and then we have 1 big. You can see here I have prepared, well, this is leftover electrolyte solution. We will use this again. Yeah. Well, actually, we might just go ahead and pour some of that into here. Let's see what happens when we crystallize that. We have not done any filtration yet. Here you can see the copper is quite an interesting color. It is actually not the way it looks before. It looks much more lustrous. Now it is much more of a dull color, indicating that it's probably oxidized.
And now it was time for everything to go wrong. First and foremost, the copper oxides were very fine and passed straight through the filter. They did this twice, in fact. This has led me to several innovations. First and foremost, I discovered that they can actually precipitate out on their own. This takes a little bit of time, but they are not very soluble in water, and the only reason they are even making the water orange is because they have been agitated, or well, in other words, they're just causing the water to be foggy, because I added some energy to it in the form of kinetic energy. Problem with distilling this is that we may have a mixture of both copper oxide and, well, that we would have a mixture of many different compounds, ranging from copper oxide to sodium hydroxide. This is not what I want pure copper oxides. We must wait for the copper oxide to precipitate out and settle down at the bottom, then decant any electrolyte solution. This leaves behind a little bit of the solution and copper oxide. Their separation would be very difficult without superior filters, such as a coffee filter. Here we are doing very unsafe practices using bare hands with what might be contaminated with bleach and sodium hydroxide. I even got some on my hand, however I cut it out because I did not feel like that is something we should put in the video, as it seems quite unprofessional. I can tell you that from the perspective of being a human pH strip, that it felt kind of basic, but not to a harmful degree. I would compare it much to having orange juice spilled on you for an extended period of time, so near the pH of citric acid. However, I would not recommend doing this yourself. In fact, I would greatly discourage doing any of these things yourself, as in fact, there's a lot of chlorine gases produced which is very dangerous, and the sodium hydroxide could be potentially even more hazardous if spilled and if concentrated, and the only reason I am doing this is because I know what I am doing. I have read a lot about this, and while I may not know anything about the final oxide product, I know how to safely produce it. Here we are putting separation method number 2 into practice. I only thought of this after crystallization, and I discovered that at the bottom of the ice was all of the copper oxides. In the future, I will probably use this method of separation even more, without the freezing and just waiting a little bit. This will allow any oxides that form to settle at the bottom and allow for me to easily decant the electrolyte solution, which I do not need anymore. I also wanted to play with some new equipment I got. These are pipettes. They are used for dropwise adding things or for adding very specific amounts of something. Though more the prior than the latter, as to add a very specific amount you may use a graduated cylinder or beaker instead, but these pipettes come in many sizes. The ones I have range from 3 milliliters to 10 milliliters. I don't remember exactly which one I used, but the two big ones have a blue thing on the back and it is much larger, so I know this is one of the smaller ones. The only reason I was using this was because I thought I would just be able to pull out clear water from the foggy solid. However, I discovered another use, which was adding them onto the drying sheet, as adding a smaller amount would allow it to dry much faster, allowing me to harvest the oxides. Although things went very wrong, and the final product was contaminated, it may not have been shown in the video. There are crystals on the drying platform. They are now present in the drying oxide, although you can see that the oxide is a mixture of different shades of blue, and also brown, or red, or orange. I do not know if the blue is an oxide or if it is a chloride of some kind, as I have seen that some copper compounds that form with chlorine are blue, and this could just be some of them. To end today's video, we will compare the pure product to the pure iron oxide I have. You can see on the left we have the copper, and on the right we have the iron. Both are brownish red. The iron would appear to be much more granular, while the copper, the tiny amount that I have, is a very fine powder. This is a quality I do not like of it, as it passes through filters and is hard to concentrate to the corner of the bag. I would like to thank you all for watching and have a great Monday.